shit slice!
Alright, welcome back. In this we're going to go over ozonolysis explanation practice problems. I made a lifetime total of $462.24. So here is what we're going to do. I'm going to go over the overview of ozonolysis. We're going to talk about ozone. We're going to talk about the recipe for ozonolysis. We're going to talk quickly about the mechanism. I'm not really going to go over this because it's not too important. I highly doubt you're going to be asked about this. Then we have a lot of practice problems to go over because I really want to make sure you guys are prepared. In addition, I am recording this video on my birthday. You will most likely watch this when it's not my birthday because I want to be uploading like 2 days later. I was thinking to myself, what is the best way to celebrate my birthday? By recording an organic chemistry video right before I go to a bar and get drunk. So here we are. So the last alkene reaction we're going to go over is ozonolysis. What we're going to be doing is cleaving the carbon-carbon bond where the alkene is and replacing it with 2 double-bonded oxygens. So we're literally taking our alkene and slicing it in half. And when we do this, we create, with these reagents, we create 2 double-bonded oxygens, carbonyls, here and here, and the molecule is now separated. That's what ozonolysis is doing. Now let's talk about ozone. You will probably not be asked this on an exam, but it's very important to know so you can understand how ozone is protecting us from from dying, and so you can educate your dumb idiot friends when they don't believe that their car emissions and ACs and power plants are bad for you. So here's what happens. Ozone is found in our atmosphere, but how is it formed? Well, the air has molecular oxygen, O2. When UV light from the sun hits O2, molecular oxygen, it creates 2 oxygen radicals. So basically splits the oxygens apart and creates 2 radicals. These radicals have unpaired electrons. Well, what happens is when one of these oxygen radicals interacts with more molecular oxygen, it creates ozone, O3. And this is what's protecting us from damage from the sun. What happens is when UV rays hit ozone, it brings it back to this form, molecular oxygen and radicals. And this cycle here is called the Chapman reaction. Chapman, Chapman reaction. This reaction is what's helping us from not dying from the sun and being burnt. That's why ozone is super important for our atmosphere. Now, this reaction is happening in the stratospheres. The troposphere, where we're located at ground level, it's harmful. Ozone is harmful. Let me explain why. Well, when nitrogen monoxide or nitrogen dioxide, which is produced by car emissions, power plants, airplane stoves, all that kind of bad stuff, comes into contact with UV rays, it actually creates oxygen radicals. So the nitrogen and oxygen, so let me do this. Nitric oxide and nitrogen dioxide. So when UV rays come into contact with these, it splits up to the oxygens, create the radicals. Now, the radicals are going to go form with molecular oxygen to create ozone. The ozone that's being created on a ground level, we breathe that in. And that's damaging. Our body cannot metabolize ozone correctly. And that's how cancers cause lung damage and, damages the plant life. So that is why ozone is dangerous on the ground level, but it's amazing for us in the stratosphere. So very important to know. Okay, let's talk about the recipe. So what the first step of the reaction, well, first we need an alkene. The first step of the reaction is ozone. What this ozone does, it gets rid of the alkene and adds the oxygens. Step 2 is you need a reducing agent, like something like DMS or zinc in water. And what this does is it splits the molecule in half. That's what it does. Now, the mechanism for this, you cannot show this. It's too advanced and it's too complicated, so you don't learn that part. You only really need to know, we don't even really need to know the first part either, but I'll quickly explain it. You will never, I highly doubt you'll be asked this on an exam, like to draw the mechanism. You'll just probably be asked, what's the product or what's the reactant? Now, here's the trick. Anywhere you see an alkene doing ozonolysis, erase the middle of it and add 2 double bonded oxygens to each side. So literally what you're going to do is take your eraser. This is why you don't do organic chemistry in pen. Erase this, and then you're literally adding a double bonded oxygens. Oops, that's too fat. Like that and like that. And now that will literally be the answer. That's the reaction. So that's how you do it. Okay. Here's the mechanism. I'm not going to go over all of this. What's really happening here is the pi bond's going to attack the oxygen. Oxygen has too many electrons in the bonds, so it's going to give it to this central oxygen. Then it's going to cause these electrons to attack here, and then we get this initial ozonide. It's kind of like our oxymercuration, demercuration in a way. No carbocation on the actual molecule here. And then we do basically 20 million different arrangements, and we get this. Really, don't worry about this. It's not really important. What's really important is the practice problems. Okay, predict the products of the following ozonolysis reactions. We have this, and then our reagents here. So anywhere you see an alkene, you will do this. Not just one, not just two, not just three. You do all of them, depending what what's stated. So here, you erase this. I'm just going to show for this one, but erase this, erase this, erase this, and then add our oxygens here. And then one here, and then here. It's so bad, but here. This is the whole point. Okay, this is what it's going to look like. So we split this up, and we added our 2 oxygens here. Same for here. We had our double bonded oxygen here. And then this gets separated as a second molecule here. And then we are left with this. Because there is a hydrogen here. This carbon has 1 bond, 2 bonds, 3 bonds, so there's an invisible hydrogen here. Make sure you draw in the hydrogen. You don't really need to, but it's good to know, just in case your professor is picky. But there you go. Okay, B. We have 2 alkenes. To look at this, they're symmetrical. So what we're literally going to do is split this molecule in halves. So erase this. And then our oxygen is going to go here, 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 and here. Like this. And notice there's a gap here. So we have 2 separate molecules here. There's a gap. So we have 2 separate molecules. Pretty easy, right? It shouldn't be that bad. Hopefully it's not that bad. Oh, what about this one? Ozone and DMS. Okay. Even though this looks so complicated, you're like, what the fuck is this? All you need to do is do exactly what we've been doing. Erase this. Get rid of this. Do this. And then put our oxygens here. Make sure they're double bonded. And then that's our answer. And I just drew in the hydrogen there just to show you, right, that there's a missing, right? If you do the double bond here, right? So this carbon has 1, 2, 3 bonds. So there must be a hydrogen here. Same goes for the other side. You don't have to draw in the hydrogen. I'm just showing you that, it's there. And what makes this also important is when you do ozonolysis, there's no stereochemistry. There's no wedges or dashes because this carbon where you're adding the double bonded oxygens, well, this is a double bond. There's no 4 different groups. So it's impossible to be on wedges or dashes. It's never possible. So that makes life so much easier, right? Okay. Ooh, tell me the reactants of the following ozonolysis reactions. Okay. You see that we have here and here. There's nothing else being shown. That must mean these were originally joined together. Because remember, in ozonolysis, we're breaking apart, we're cutting apart an alkene and separating them to create two double bonded oxygens. So these are now separated. That must be in the reactants that must have been together. So that means this carbon and this carbon must have been together, joined by an alkene. Here is the trick. So there is a ring. The reactant will have a ring in it. The cheat code is count the number of carbons between both carbonyls, and that's how many carbons are in your ring. So you start from here, right? Because this is the first oxygen and this is the end. So 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. Our ring will have 5 carbons. And then everything else is not part of the ring. Like this. So this is branching out here. This ethyl group is here. And this methyl group is here. The ring, 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. That's the trick. That's the easy way of doing it. Hopefully you can see that. Because let's do B. Okay, we have this. I'm also telling you an additional piece of information. I'm telling you the reactant is going to have 10 carbons. You will notice that this product only has 5 carbons. 1, 2, 3, 4, 5. How is that possible? Well, you'll also notice that we're missing another carbonyl. Where's the other double bonded oxygen? Well, if we have 10 carbons on the reactant side, we only have 5 carbons on the product side, and we only have 1 carbonyl. That must mean this is a duplicate. There should be 2 of these. So in reality, there are 2 equivalents of this. I just didn't draw it in because I want to trick you. 2 equivalents. Spelled that completely wrong, but 2 equivalents of that. Okay, that must mean that we have an identical one of this, another identical product. I'm going to just copy and paste it here like that. And then this carbon and this carbon are going to join together. So they're going to be facing each other like this. Notice that the alkene, these double bonds are not in the ring themselves. They're outside the ring. So we're joining them together like that. This stays as it is, right? You're not modifying this at all because the alkene's not there. The alkene's on the outside, so that's all we care about. So we form a bridge. Okay, challenge problem. The following molecule can undergo ozonolysis. When chemists analyzed the product, they noticed that the aromatic ring did not react. Draw me all the products. Okay, so what this is saying is that we have a bunch of alkenes here. The ones in the ring do not react. I'm telling you this. It's not. It's in the problem. I'm telling you, it's not reacting. If it was not stated, then it would be reacting, and then you would do 50 million different products. But they're not reacting, so don't worry about anything here. This is the reactant. So we see a double bonded oxygen here, it's not going to do anything. It's left alone because this is the reactant. This is not the product. And the reactants, we only care about the alkenes, only carbon-carbon double bonds, nothing about carbon oxygens. So this does not matter whatsoever. We have an alkene here, an alkene here, an alkene here, and an alkene here. So these are all the ones that are going to be doing the splitting. So Should I just show, what should I do? Should I just show you the answer? Yeah, let me just show you the answer. That'd be easier. Okay, we have all this. So, you might be fooled when you look at something like this or like this. This is like is the usual stuff, right? Like you split this in half and you put the you put the double bond oxygen on either side. So you get this and you get this. For here, you get this and you get this. Right, because if you split this up, you split this up like that. This is CH3, this is CH3. Right, you get this. That's exactly what we get here. This is this piece, and this is just this piece. Okay. Same thing goes from here. This is identical. This is identical to this. So you get this, and you get this. Okay. What may be confusing is this part, because you're like, wait a second, I don't see anything here. No, there is something there. There's a carbon there, because that's an alkene. So we have a carbon here. That means we convert it into a carbonyl, which we are going to do. Yes. We get that. And then we get the other side must have a carbonyl, like that. And then hydrogens. That's what we're doing. Same goes for here. Because you got to think about this. By default, we must make this a carbonyl, right? 2 carbonyls, because this is an alkene. So both carbons get it. Well, when you make the carbonyl, let's do it like this. Okay, we made the carbonyl there, right? That's for this. Carbon must have 4 bonds. It has 2, but what about the other 2? And that's why we fill it with hydrogens. That's why I'm showing it like this. And that's it. That's the answer. If you found this video helpful, please like and subscribe. And until next time, later.